Hey everyone, it's Mr. Wolfe here, and in this video I'm going to be going over biological concept 3. So if you look at your KUD sheet, the cardstock pink sheet that kind of has what you need to do, what you need to understand, and what you need to know, that third no category is being able to compare and contrast the structure of an atom to the structure of a molecule. And to tell you the truth, I think this slide does a really good job at showing the difference between an atom and molecule right here. So you can kind of start to get the idea of what an atom is versus what a molecule is just by looking at the picture. But I do want to go a little bit more in depth with this stuff. So let's start. And by going a little bit more in depth, we're first going to take a step back and we're going to talk about our driving question of the unit, which is where does a tree get its mass? Right? So we start from this little seedling, and then you could get a tree as big as a sequoia or a redwood, right? And where did this mass come from? It especially becomes very, very puzzling when we have this law of science, which is mass cannot be created or destroyed. So you can imagine that before right here, this could be like a really simple example of my seedling, and then my tree or the beginning of a tree is getting bigger, and that mass is obviously coming from somewhere, but the question is from where, all right? And really quickly, in terms of writing this stuff in your notes, you have a sheet, but don't worry about writing anything just yet. I'll let you guys know when you need to start writing your notes. This is just a little bit more of an introduction, providing you with context. So remember, our question is, where does a tree get its mass from? But in order to really answer that question, we're going to need to get a few things down. So a better question to ask to start to get more specific with this target is, what is matter? Right? And that's when we're going to get into atoms and molecules. Now, I'm actually going to ask a second question because I just think it provides some interesting context, which is, well, what is an air? Right? And I think this is a cool way of introducing atoms and molecules. And it gives us a little bit of a perspective too. So asking the question, what's an air? Let's start at a large scale. So this picture right here would be 1,000 meters long. Essentially, it's just like you're looking at the sky. Right? But we could obviously zoom in a little bit more. So you can kind of see my red arrow going down. Now we're at the very bottom of the macroscopic scale. Essentially, this is almost past human visible vision. This would be, by the way, a millimeters, a picture of what's in a millimeter. So think of a ruler, right, and those tiny little marks in between centimeters. All right, this picture would be fitting in between one of those or two of those lines. Right? So 1 millimeter. But we could zoom even further. And by the way, I don't know if you guys noticed, it's a little bit tough to see, but there's like these little circles in this image behind kind of like the hazy cloud. Those are going to be water vapor droplets. So let's zoom into the microscopic level, and then we could actually see our water vapor droplet now. And then we can zoom even further, and here's the surface of our water vapor droplet. And by the way, if we look at the scale, this is 10 to the negative 6 meters, which is essentially saying that you could fit, this is a millionth of a meter. You could fit 1 million of these pictures, or at this scale, into just 1 meter. So we're getting really, really small, but we're going to get even smaller. We're going to go to the atomic molecular level. This is like at the nano level. And what we see here is you see all these blue and kind of like white molecules all together. That's the surface of the water droplet that we saw before. Right? Now we're just zoomed even more, we can actually see the atoms and molecules. Right? Now keep in mind, scientists have actually never seen these atoms and molecules, but through running thousands, millions of experiments, just like the black box activity, they could start to develop a model of how these molecules look and how they act. All right. So the different kinds of molecules that are in air, here's a few. So oxygen is one, which makes sense, right? We breathe in oxygen. There's water, and we saw that a bunch of those water molecules will make up a water vapor droplet. There's carbon dioxide, and there's nitrogen as well. So what's the proportion? How much oxygen, how much nitrogen is in our atmosphere? Most of it is actually nitrogen. So the air you're breathing in right now, most of that is nitrogen. 21% is oxygen in the blue. Carbon dioxide is just a really, really small amount, and water vapor, it just varies depending on the humidity. Okay? And then argon is another type of element that I didn't talk about before, but that is another molecule that's also in air as well. All right. So I think that gives some cool perspective in terms of you have air, which seems sometimes like it's empty space, but it's obviously not. It's made up of matter. It's made up of mass. So now let's dive back into that question. what is matter, what is mass. And really quickly, you'll notice that on these slides that some stuff is in red. So now I'd like you all to start writing in your notes. So anything that's in red, write down. Obviously, there's going to be a lot of stuff on these slides, and I want you to write down everything. So the stuff that's in black, just don't worry about it. Remember, you could always go to these Google slides later as well. All right. So matter is anything with mass and volume. And so AKA, matter is made up of atoms. So then, well, what is an atom? So an atom is just the basic unit of matter. I'm sure you guys have heard that before. Another good way to describe it, it's the smallest fragment of an element that retains the properties of that element. So what the heck does that mean? I think this is a really good example. All right, so a diamond is actually made out of just one type of atom. It's just made out of carbon. All right, so now let's say I take that diamond and I were to cut it. Right, and then I have these diamond pieces. All right, those diamond pieces are still made out of carbon. And then imagine that I would cut those pieces even more, right, into even tinier, tiny microscopic diamond pieces. They would still be carbon, or made out of carbon atoms. All right? And then imagine that somehow I was able to cut them down to finally I'm at just one carbon atom. All right? Even if I have one carbon atom, all right, that's still carbon. Right? Now let's say though that I were to break that carbon atom, break it down even further, that it would no longer be carbon. So an atom is the smallest level that we could get to where that object retains those specific chemical types of properties. Right? Now, an atom is the basic unit of matter, but you can see in this picture that an atom is actually made up of even smaller particles. And so we call these things subatomic particles. So you think of the word atomic like an atom, and the word sub is a prefix which means smaller than. Another way that I like to think about it is a submarine is underwater, so it's almost like we're not going under, but we're getting smaller and smaller and smaller when we're talking about these particles. Okay. Hopefully some of this stuff is a review as well. So in terms of what atoms are made up of, with every atom there's always a nucleus, and in that nucleus you have protons and you have neutrons. Protons are positively charged, neutrons are neutral. They don't have a charge, so sometimes I just represent that by the circle. All right. Now, orbiting and zipping around the atom are electrons, and electrons are negatively charged. All right. So don't worry about writing this in your notes, but I think that this is incredibly fascinating and just something I like to add into the slides. Atoms are mostly empty space. All right? For example, if an atom was the size of a football field or a football stadium, right, not just the field, the nucleus of that atom would be the size of a marble. So imagine a marble placed up this 50-yard line right here. All right? So imagine all those protons and neutrons, all of them together would make that marble right here, okay? And then an electron would be a sesame seed. So just imagine like one of those tiny seeds on like a burger bun, right? And it would be as far away as the very like rafters, the top of the stadium, zipping around. So then imagine you took away the stadium, but you still have that distance and everything. All of that would be empty space. So most of an atom is really just empty space. But there are these particles, right, that take up space and have volume, and that's the matter part. Right. So we have atoms. Now let's talk about elements. And I'm sure you guys have seen the periodic table of elements before. And really what this is just showing is just different types of atoms. Okay? So all atoms are made up of those subatomic particles. They have a nucleus, protons, neutrons, and electrons. But you could have different types, like a carbon atom, an oxygen atom, hydrogen atom, a gold atom, okay? And this is just a way to kind of organize all those different types of atoms. It's a way to organize all of these different elements. All right. So what makes a carbon atom and a carbon and oxygen? Especially if they're all made of the same stuff, right? Protons, neutrons, and electrons. It turns out it's just based on the number of protons. So on the periodic table, there's a lot of information here, but all you need to worry about is this number at the top left corner. All right? So for instance, carbon has 6. Right? What that means is that a carbon atom has 6 protons. And if we move over to oxygen, you see an 8. That means that oxygen has 8 protons. So what gives oxygen its properties and makes oxygen oxygen is the amount of protons it has. And then in carbon, it has 6 protons, so that makes it carbon. So if carbon all of a sudden had 5 protons, well, it wouldn't be carbon anymore, right? It would be boron. So that's how we can figure out what the different types of elements are and what makes them different. Okay. So we've talked about atoms, what make them up. We have different types of atoms, and those are called elements. But what's the difference between an atom and a molecule? And this is the purpose of the video, right? And I really like this slide. It's simple in terms of answering the question. Really, an atom is just one atom. And a molecule is when you have two or more atoms, and they're bonded together. Okay, so you could have a molecule that's just two atoms attached to one another, or you could have a molecule with thousands, if not millions, of atoms bonded to one another as well. All right, that's it. Okay, so when we're going to be talking about molecules and how atoms bond together in this class, we're going to be talking about organic molecules. And when I say organic, think of just molecules that are in living things. And you could maybe imagine how complicated some of these molecules could get, right? If you have just these different atoms and they could bond in so many different ways. But even though that might get complicated, there's really, really simple rules for figuring out how these atoms bond to one another, right? And so one way to remember it is the phrase honk, okay? So hydrogen only makes one bond. Oxygen only makes two bonds. Nitrogen only makes three bonds. And carbon will only make four bonds. And so you can kind of remember hydrogen's the first letter, so one bond. Oxygen, second. Nitrogen, third. Carbon, fourth. Okay, so let's show an example of this in terms of what I mean by it. All right, so here I have different molecules, right, because these are all examples of atoms bonded to each other. There's more than two atoms in all of these cases, so these are molecules. So my first one's H2O, that's water. So if I wanted to draw this molecule, this is how I would go about doing it. I'm just going to show it to you guys. You have two, first I want to look at this formula. H2 means I have two hydrogens, and in my drawing I have two H's, so perfect, and I have an oxygen as well. All right, so at least I have the amount of atoms that my molecule says I should have, but remember I need to follow these bonding rules as well. So did I follow the bonding rules in this case? And it looks like this hydrogen atom only has one bond, so awesome. This hydrogen atom only has one bond, awesome. And this oxygen atom is making two bonds, perfect. I've hit those honk rules. All right, so this would be how a water molecule is structured. All right. By the way, if you were to make this is how actually it is. There's oxygen and the hydrogens kind of go here, and they're not flat. But you do not need to worry about having that type of detail. If you kind of drew just the hydrogens going flat, I'd be fine with that as well. All right, so here's hydrogen. Again, it's H2, right? So this is a hydrogen molecule, and they're bonded together. Remember the rules that hydrogen only makes one bond. This hydrogen atom is only making one bond. This hydrogen atom is making one bond. Perfect. Okay, so let's go to oxygen. It seems easy, right? So here I have two oxygen atoms to make up one oxygen molecule, because it says O2. And then I have a bond, but all of a sudden my rule has been broken. Remember, oxygen needs to make two bonds, and in this case, this oxygen is only making one, this oxygen is only making one. So a lot of students think, oh, I'll just put a bond to the right of this the right oxygen, and I'll put a bond to the left of the left oxygen. Well, you can't do that. Like, a bond has to be attached to another atom. So what do we do here? Well, it's possible, and this happens all the time, is that atoms will make a double bond. So you could do this too. And so notice that this oxygen now has two bonds, and the oxygen to the right also now has two bonds. So let's try CO2, right? Carbon dioxide. So it has two oxygen atoms and one carbon atom. So I could start it off by just doing this, right? Where I know that I'm going to have this many atoms and that they're going to be bonded together, but then I want to make sure that my rules are present as well. So for instance, I have oxygen, and that is only making one bond. It needs to make two. Carbon needs to make four bonds, and it's only making two. And this oxygen needs to make two, and it's only making one. But again, remember, I could use that double bond trick from before. So if I add double bonds, notice that this oxygen is now making two bonds. This carbon is now making four bonds, which it should. And this other oxygen is now making two bonds as well. Okay. So here's the last slide, and it's just some more examples of how hydrogen only makes one bond. I made sure to just bold the hydrogen. All right, how oxygen always only makes two bonds. Nitrogen makes three. We didn't talk about nitrogen, but here are some examples. And then carbon only makes four bonds. So here's some examples. All right, I think this is a helpful reference on the Google Slides. So this is it for that biological concept 3 in terms of atoms versus molecules. Thanks for watching. and see you soon.